Good afternoon. I am Christan Cyrus Hadlocon, and I am taking up Bachelor of Science in Mechanical Engineering. I am a third year mechanical engineering student, and I am going to discuss what is a capacitor. So a capacitor are electrical components that store, filter, and regulates electrical energy and current flow are one of the essential passive components used in circuit boards. So, capacitors are primarily used for storing electrical charges, conducting alternating current, and blocking or separating different voltages levels of direct current source. So the unit of capacitance is the farad. So the unit for capacitance is farad. 1 farad of capacitance is 1 coulomb of charge is stored on the plates when 1 volt is applied. So below you can find the equation. 1 farad is equal to 1 coulomb over 1 volt. So okay, 1 coulomb represents or equivalents to 6 times 10 raised to the power of 19 electrons. So you can see that is the introduction or the definition for a capacitor. So next slide would be construction of a capacitor. So construction of a capacitor, the simplest form of a capacitor is a parallel plate capacitor. Again, parallel plate capacitor. So you can simply imagine parallel plates, maybe 2 plates parallel to each other. So that might be the easiest way to imagine what is a parallel plate capacitor. So, and its construction can be done by 2 metal plates that are placed parallel to each other at some distance. So again, I am right. So parallel plate capacitor are its construction is made up of 2 parallel plates and 2 metal plates parallel to each other at some distance. So if a voltage source is connected across a capacitor where the positive voltage or positive terminal is connected to the positive terminal of the capacitor, and the negative terminal of the voltage is connected to the negative terminal of the capacitor, then the energy is stored in the capacitor is directly proportional to applied voltage. So you can see in the next slide that the construction of a capacitor. So you see the voltage there. The green colored rectangles represents the conductive parallel plates, or the 2 metal plates parallel to each other. So you can see the electrical charge, the positive terminal of the voltage is connected to the positive terminal of the capacitor. The negative terminal for the voltage is connected to the negative terminal of the capacitor, and on the left side it shows the symbol of the capacitor. So the parameters of a capacitor. The amount of capacitor C for a parallel plate capacitor is determined by the equation C is equal to E times A over D, where A is equal to plate area, D is equal to distance between plates, and E is equivalent to is defined as dielectric material constant. So again, the equation would be C is equal to dielectric material constant times area of the plate all over the distance of the plates, distance between plates. Also, note that E is equivalent to relative dielectric constant times dielectric constant of vacuum. So this could be ER times E raised to the power of 0 times 0. So where ER is a plane number and E0 is equivalent to 8.85 times 10 raised to the power of negative 12 F over M. This general formula shows that the larger the plate area, the larger the capacitance value. So simply saying that if the metal plate has a larger area, so it could give a bigger capacitance, larger amount of capacitance to the capacitor. So next would be the smaller the distance between the plates. So two metal plates parallel to each other, and they are the distance between them are short. I mean just near or just not that far, but not that long too. So this could help. This could give the capacitor a higher or larger amount of capacitance. So next, the larger the dielectric constant of the insulating material, the larger the capacitance. So those would be the parameters of a capacitor. So in the next slide, you'll see the figure for capacitance parameters, parameters of the capacitor. So you see, figure the distance between two plates where the dielectric with permittivity is equal to E, and the negative and positive terminals, conductive plate with the area A. So that's the figure for the parameters of capacitance. Properties of a capacitor. So an ideal capacitor has exactly desired capacitance value, and it is a perfect insulator. However, practical consideration must be taken into account for both the capacitance value and amount of insulation provided by the given capacitor. So the first properties of capacitor: the capacitor can store electric energy, as discussed earlier. So it has been already discussed in the introduction. The capacitor can store electrical energy. So electric energy, rather. So next would be the capacitor can separate different DC voltage, direct current voltage levels from each other, but also conducts AC current, also being discussed in the introduction already, earlier. So in general, the higher the frequency of AC voltage, the better the capacitor conducts the AC current. So that would be the properties of a capacitor. So next would be a capacitor water tank analogy. So you can consider, so this might be weird to hear that a capacitor water tank analogy. So how does it connect a capacitor from a water tank? So here it will be discussed. So consider two water tanks, one larger and one smaller, connected to each other with both a pipe and a membrane closing the pipe. So there would be a bigger tank and smaller tank, and they are both connected with a pipe with a membrane between that closes the pipe. I mean, there's a rubber 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 membrane that closing the pipe. So you can really you can imagine what it looks like. So this membrane acts like a capacitor. So you see, the membrane that closes the pipes acts like the capacitor, separating the high water level in the larger tank, high voltage, from the low water level in the tank, in the smaller tank. So basically, so you can picture us. So again I'll discuss about it. So first, a bigger tank in electrical, that would be a higher voltage, and the smaller tank represents as the lower voltage. So the two of them are being connected with the pipe, and that pipes is being there is a rubber membrane that closes the pipe. So this rubber membrane represents as the capacitor. So simply, it functions as it helps, it stabilize the it stabilize the water tank, the levels of the tank from higher and lower. So it stabilize the water, the water from the two different volume tanks, the higher and the lower. So thus alternating movement or voltage is transferred through the membrane or the capacitor, although no water or direct current is flowing from one tank to another. Tungod kay ang rubber membrane, it closes the pipe, so it acts like the capacitor. So it stops the water from the higher tank to transfer from the lower smaller tank. So charge and discharge, charge or discharge behavior for a capacitor. So when a DC voltage is applied to a capacitor connected in series with a resistor, the capacitor begins to charge at a rate according to the applied voltage. So being discussed in the previous discussion, you can understand what the first statement means. So the next, again, when a DC voltage is applied to a capacitor connected in series with a resistor, the capacitor begins to charge at a rate according to the voltage applied. So the state of charge relative to its final value, the total resistance, the series resistance, and its own capacitance. The product of the resistance and capacitor is referred to as time constant. So you can find it in the slide. T is equal to R times C, or time constant is equivalent to resistor times capacitance. So of the circuit, actually it is the time required to charge the capacitor by 63.2% of the difference between the initial value and the final value. So therefore, it is the time that is being required to charge a capacitor by about for 63.2%. So hence the value of a charge plotted against time follows the curve shown in figure 6. So in figure below. During this time, the charging current follows the red curve also shown in the figure. So charging a capacitor through a series resistance. So this is the diagram for the charge and discharge behavior. So there's a perpendicular line at time, and for the time for the x-axis, and for the y-axis would be charge in capacitor, charging current. So the charge of the capacitor at any time t is calculated by the following equation. Q is equal to capacitor times voltage times 1 minus E minus T over RC. So the charging current decays according to the equation. I is equal to VR times E minus T over RC, where E is a constant 2.7182818, the so-called natural numbers, or the base of the natural logarithm ln x, ln to the quantity of x. Many physical and even economical phenomena can be explained by the described using exponential or logarithmic functions. Note that in the practice, the charging current does not reach zero and tends towards a small finite value equivalent to the capacitor leakage current. Similarly, the time constant T is equal to R times C also governs the time to discharge the capacitor through the series resistance. So that would be the charge and discharge behavior. So next would be capacitor technologies. Capacitor technologies can be divided in two basic groups. So first one would be the electrostatic capacitors and the electrolytic capacitors. So first, electrostatic capacitors are symmetrical non-polar constructions. So materials such as plastic film and ceramic are used as a dielectric, while a variety of metals are used as electrodes. Since these parts are not polarized, they can generally be inserted into a circuit without regard to the points the terminals are connected, while the electrolytic capacitors, on the other hand, do have a asymmetric and polarized constructions. Electrolytic capacitors utilize an electrolyte which may maintain the dielectric layer and also create the negative connection or cathode. Metal foils or powders such as aluminum and tantalum are used to form the positive connections or anode, known to be anode. The dielectric layer is created by forming a thin oxide of the metal anode. So typically, the benefit of using a electrolytic capacitors is that they can have relatively large capacitance values in a reasonable size. So una siya ay advantage or the benefits of using a electrolytic capacitors. While the electrostatic style capacitors are generally used for small or precision capacitance values. So you can see the difference between the two. You can see the usage between the two. So on the next slide, you can see the overview of capacitor technologies. So you can see there it's like a, how can I say this, a tree diagram from the capacitor down to variable and fixed, and under the variable there's trimmer, and under the fixed there's a lot more. So non-polar, polar, so under polar electrolyte, so non-polar, glass, and so on and so forth, ceramic. And under the polymer film there's another one, foil, metallized. So under ceramic there's another, by ceramic, PME and BME, SLC, MLCC. So, and they also have two under class 1, class 2, class 1, class 2. So under the polar, there's the electrolytic. Under electrolytic, the aluminum, tantalum, EDLC. So under aluminum and tantalum there's three. The MnO2, poly, then wet, MnO2, poly, and wet. So there's both the same. Next one would be the uses of capacitor. So first one would be decoupling. So what is decoupling? The most prevalent use of capacitor. So decoupling is the most prevalent use of a capacitor is to decouple a system. So decoupling. So that means the decoupling is one of the most prevalent use of a capacitor. The most prevalent use of capacitor is to decouple a system, such as integrated circuit, from such changes including transfer of energy within the power supply. Connecting a decoupling capacitor between supply voltage connection and ground in a integrated circuit IC close to the IC itself helps maintain a stable voltage level and supply fast power to the IC when needed. So that would be for the decoupling under the uses of capacitor. So next one would be filtering. So under filtering, the second for the most common capacitor application is the filtering. So filtering, the filtering is to remove signals at unwanted frequencies by exploiting the capacitor's inherently high impedance at low frequencies and reducing impedance at higher frequencies. A resistor capacitor RC filter can be designed to remove high frequency interference such as noise in analog signals, or to protect circuitry unwanted AC voltages. Applications includes Class AB amplifiers, AM radios, and cellular telephones. Filtering is also widely used in switch mode power supply systems and Class D amplifiers to prevent switching noise or from causing interference or impairing system performance. So that would be the use. One is the second for the most common use of application for capacitor, the filtering. Next one would be coupling. Coupling, because capacitor do not conduct DC, again previously discussed, they are often used to separate different voltage levels because voltage mo direct current or AC current. Capacitor is conductor of AC current. So used to separate different voltage levels from each other by blocking DC voltages. Since AC signals can pass through capacitors, these properly used in circuits such as multi-stage amplifiers, signals are allowed to pass through, but to separate voltage levels because of the DC current. The capacitor's ability to remove a DC offset voltage from a alternating signal is also valuable in equipment as an electronic meters. So the usage of the capacitor coupling is the third one, and it's very useful also. So it states there that capacitor can be useful in so many ways, especially in the use of coupling to separate the unwanted signals and to remove DC offset voltage. So next one would be oscillators. Together with inductive components, capacitors can be used to build oscillators for generating accurate sinusoidal signals. Oscillators are utilized for a simple timing in RF circuit or in musical instrument amplifiers, including synthesizers and electric guitars. So all of us seen already what is a electric guitar. So capacitor is also important in electric guitar because it's used as oscillators. So an inductor capacitor oscillator uses the inductor to alternately charge and discharge the capacitor, thereby setting up alternating signal with a frequency that is dependent on the capacitance and inductance values. An RC oscillator uses the capacitor to induce a phase shift by virtue of the fact that the output voltage of the RC circuit leads to the input voltage by a phase angle, which in practice is somehow less than 90 degrees. So that would be the four commonly uses of a capacitor. First is the decoupling. Next one would be, second one would be filtering. Third one would be coupling, and the third one would be oscillators. The different major capacitor applications. So there are four major capacitor applications. First one would be decoupling. So again, it has been recently discussed. Decoupling enables sudden transfers of current or energy while maintaining stable voltage levels. So that would be the major capacitor application. So decoupling is one of them. So next one would be filtering. Again, filtering was stated before that it was the second most common application of a capacitor. So filtering removes or reduces unwanted AC voltages in applications such as AM radios, cellular telephones, or IC switching noise applications. So in our phones, so capacitors application there is to filter the unwanted AC voltages. Third one would be coupling. Blocks DC and passes AC component, for example in smart meter applications. So the third one for the major capacitor application is coupling. And the fourth one would be timing and wave shaping. Timing and wave shaping sets delay time in systems such as windshield wipers. So that would be the four major different capacitor applications. So my references are on the next slide, and you can visit the link so that you can read more about what is the capacitors and its parameters, constructions, properties, charge and discharge behavior, uses, etc. There's a lot more to learn, and thank you once again. Thank you for listening. Again, thank you. Have a good day.